Howdy, Bryan Vikings. We're here to talk about the ionization constant of water and the pH calculations. So let's review what an amphoteric compound is, and it's any species that can act as an acid or a base. Water is the best example because in this equation, it is actually receiving a proton from sulfuric acid to create the hydronium ion and hydrogen sulfate. These are my conjugate acid and conjugate base, but in this case, water is acting as a base. Now, in this case, water is actually donating the proton to the ammonium molecule and creating the ammonium ion and the hydroxide ion. Now, in this case, water is acting as an acid because it is donating a proton. So it acts as an acid and a base, therefore it is amphoteric. Now, just to test your skills, there is a process of deprotonating phosphoric acid. It has 3 protons and it takes 3 reactions to deprotonate or remove all of the protons off of it. Now, identify all the amphoteric compounds that are in it. Pause the video and try it. You probably figured out that the waters are amphoteric because I just talked about that, but there are a few others. This one right here is amphoteric because it has been, it is the product of a 1 deprotonation, which means 1 proton has been removed, but according to this reverse arrow, it can actually gain another proton back and go back to being phosphoric acid. And we will recycle this same product as a reactant over here, and it will create a new one. This one is also amphoteric. So there are multiple amphoteric compounds, not just water. So you need to be able to look for them. You need to ask yourself, can it gain or receive one more proton? And you really want to look for the charges that are available to you. Now, we have discussed electrolytes before as water is, and I've told you that water is a non-electrolyte. Well, it is somewhat true that it will electrolyze completely, somewhat, is because but it is an extremely weak electrolyte because it will undergo what we call auto-ionization or self-ionization. One water molecule will share a proton to another water molecule to create the hydronium and hydroxide ions, but they will also pass the proton back, and end up back here at the reactants. Now, there are far more reactants than there are products. You cannot tell that from this reaction, but these concentrations are very small, and that's why it's an extremely weak electrolyte. Now, since these concentrations are actually known because we can measure the conductivity of the hydronium concentration and the hydroxide concentration and find out that they are both 1.0 times 10 to the minus 7 in water, 10 to the minus 7 moles per liters, or molarity. Now, anytime you see brackets here that are in the left side, these brackets will mean that these brackets mean concentration. So anytime you see brackets in chemistry, I'm talking about concentration in molarity. So both of these right here. Now the product of the two concentrations of the ionization, it will give us the ionization constant of water, Kw. Remember K for constant. That's convenient, right? So Kw is the hydronium times the hydroxide. Now I said before that these values are 1 times 10 to the minus 7 times 1 times 10 to the minus 7. Since both of these 10s are the same bases, we can just add the exponents and get 10 to the minus 14. This is a constant value at 25 degrees Celsius, and it will not change as long as you are at 25 degrees Celsius. Now we can use that equation to be able to calculate the other one. So whenever you have an acid or a base, you are going to have some of the hydronium ion, you are going to have some of the hydroxide ion. And if you know one, you can calculate the other. So if I know that I have 1.0 times 10 to the minus 7 of hydronium, I need to use my equation, and then I need to plug in my values right here. Ignore this that's over on the right. I need to plug in this value here, over here, and then my kW is a known constant. And then once that's done, I need to divide both sides by 1 times 10 to the minus 7. They cancel out. So 10 to the minus 14 divided by 10 to the minus 7 is going to be 10 to the minus 7. Okay? Now, is this acidic, basic, or neutral? Well, I can tell that I have the same concentration of hydronium as I do hydroxide. They have the exact same number. So if I have the same amount of acid as I have of base, that makes it a neutral compound. In the next one, I'm going to give you the same type of equation, except now it's 1 times 10 to the minus 11. We use the same formula, and we'll plug in the same values right here. So now we'll just take this 10 to the minus 14 divided by 10 to the minus 11, and it will give us 1 times 10 to the minus 3. Okay? Notice how 10 to the minus 11 and 10 to the minus 3, if you add up minus 3 plus minus 11, it equals minus 14, right? So that should make sense. So now ask yourself, is this acidic, basic, or neutral? We have the hydroxide concentration and we have the hydronium concentration. This is my acid and this is my base. Which one do I have more of? Well, I have more hydroxide than hydronium. This one is closer to, this power is closer to 0, which means I actually have more of it. So that means that it is basic. Go ahead and think about how making this thing closer to 0 makes you have more of it. Make sure you understand how that power system works. Question 3. We are just going to do the backwards way now, and now you have your hydroxide is 1.5 times 10 to the minus 4. So I use the same equation, I plug in the same numbers in a different area, but it's going to be the same math. Take Kw divided by this will now give me my hydronium concentration of 6.67 times 10 to the minus 11. Now ask yourself, is this acidic, basic, or neutral? I have more base than I have of hydroxide, so it is basic. Okay. Now by now you are figuring out that even if it is a basic solution, you will still have some hydronium concentration, and that's what this idea is. It will be much smaller than the hydroxide, but there will still be some there. So now that's the whole point of us calculating this. And then one more, just for show, I want you to try to do this one yourself. Pause the video, and then I'll show you the answer. Did you get this answer? This should be an equal sign right here, but your hydroxide should equal 2 times 10 to the minus 9. So ask yourself, which one is it, acidic, basic, or neutral? It's going to be acidic. Okay, so let's move on to the pH scale. So a bunch of scientists have kind of figured out is those numbers that you were just using are pretty cumbersome, right? All of these numbers right here, the 10 to the minus 9, 10 to the minus 10, all that stuff. So we decided to try to get rid of that. We tried to get rid of this negative and get rid of this 10, this exponent right here, and just end up with a nice, convenient whole number. And that's what the pH is. So to do that, all we're doing is going to transfer from this number to this number. And the mathematical calculation of that is the negative log of the hydronium concentration. Now this is log base 10. If you have never heard of a logarithm before, that is okay because you are just going to type a button on a calculator. That's not that big a deal. Now, if you have heard of a logarithm before, this is not near as hard as what you've done in Algebra 2. All you have to do is use log base 10. okay? Log base 10. So you will be given the pH is the negative log of my hydronium concentration. The pOH is my negative log of the hydroxide concentration. And the pH and the pOH have to add up to 14. Now, if you may have noticed, the P actually means a mathematical calculation of negative log. So if it's pH, it's the negative log of H. If it's the pOH, it's the negative log of OH. Okay, that's what the P means. P means negative log. Example number 6 in your notes says to calculate the pH and the pOH of a solution if the hydronium concentration is 3.7 times 10 to the minus 8 molar and describes the solution as, and I want you to describe the solution as acidic, basic, or neutral. You have your given information already in front of you. So let's get started. We know that let's go ahead and find the pH first because that's the easiest one to do since we already have the hydronium concentration. So I take the negative log of 3.7 times 10 to the minus 8. I ask the calculator what that is, and the calculator tells me it's 7.43. That's very convenient. So now ask yourself, is that greater or less than 7? Well, it's greater than 7, so it must be basic. Okay? Now the next step is, well, because it's greater than 7. Now the next step is to actually try to find out the pOH. Since I already found the pH, that is going to be 7.43. 7.43 plus the pOH is going to equal 14. So I can just rearrange my variables to get this equation right here, but that's where this one came from, right? This one came from here. And then, so it's really 14 minus 7.3. I find my pOH is 6.57. These two numbers must add up to 14. All right, always, always, always. Okay. Next question says calculate the pH and pOH of a solution if the hydroxide equals 8.5 times 10 to the minus 10 molar and describe the solution as acidic, basic, or neutral. We have our three known pieces of information, and let's get started with the pOH equals the negative log of my hydroxide concentration. I ask my calculator what it is. It tells me it's 9.07. Now be careful. A lot of students will see this and then they'll ask themselves if it's greater or less than 7 and then stick with one of those things. But you are in pOH world right now. So pOH world is backwards from pH world, okay? So you may want to wait until you get to the pH before you make this adjustment, okay? Be careful. So I'm going to find my pH from my formula that's over here because I know that the pH and the pOH have to add up to 14. 14 minus 9.07 is 4.93. Now ask yourself, is that greater or less than 7? It's less than 7, so that makes it acidic. Very nice. Now let's go one more step and let's take the anti-logarithm. Now this is the backwards of a logarithm. If I know the pH, how can I find the hydronium concentration? Or if I know the pOH, how can I find the hydroxide concentration? So I'm going to take the opposite of a logarithm. This is actually easy to do. Because if I have the pH equals the negative log of my hydronium, I'm going to move the negative over to the other side. Okay? What I'm going to try to do is I'm going to pretend that this is like my X value, and I'm going to try to isolate this hydronium concentration. So I move the negative to the other side, and now I am actually going to raise both sides by the power of 10. I am allowed to do that because algebra rules say I can. So I have 10 to the minus pH and 10 to the log of H3O plus. Those of you who have taken logarithms before know that 10 to the log will cancel this out. And this H3O plus will come in front. So 10 to the minus pH is the hydronium ion concentration. If you did not understand one bit of that, that is okay. All you need is this formula down here. You do not have to prove one bit of math in my class. So there's your given information. This is already given to you. Your hydronium and your hydroxide concentrations are already there. So calculate the hydronium and the hydroxide concentration of a solution with a pH of 3.3. So I know that I'm going to use this equation. I just type in 10 to the minus 3.3, and I find that it's 5 times 10 to the minus 4. Okay? Now, an easy thing to do is to find the pOH. Okay? Find the opposite of pOH. All right? Of this using not that. Don't do that. Do this. Do pOH equals 14 minus 3.3 equals 10 to the minus 10.7. Okay, sorry. We know that the pH and the pOH have to add up to 14, right? So 14 minus 3.3 is going to be your pOH, right? Right? Okay. So now I can just find my hydroxide concentration by using the same formula, 10 to the minus 10.7, and I find out that my molarity or my concentration of hydroxide is 2 times 10 to the minus 11. This area up here is an optional way to do it. It's using the kW value that we have done before. Um, that's not my preferred way to go. I try to avoid kW as much as possible. I'd rather do this because I'd rather just subtract. It's up to your choice. It doesn't matter. Both ways are correct. Now, exact same kind of problem. I wanted you to calculate the hydronium and the hydroxide of a solution with a pOH of 5.3. So I know the pOH, so my hydroxide concentration is 10 to the minus 5.3. So I find it's 5.10, 5 times 10 to the minus 6. Now I'm going to calculate the pH because I know the pH and the pOH add up to 14. So 14 minus my pOH, which is 5.3, will give me my pH. So now I just have to take 10 to the minus 8.7, and I will find my hydronium concentration, which is 2 times 10 to the minus 9 molar. This is a very easy way to kind of condense everything that I've just taught you into one slide. You can now move between pH, pOH, OH, and H+, also known as H3O+, into different ways. Notice you can never go across, you can never go diagonal, but you can always go from one to the other just using these calculations. I won't give you this slide on the test, but but I will give you the formulas which are already there. Okay. Go ahead and get practicing on your worksheet that's already assigned to you in your worksheet packet. There should just be one side to this, so get it done. Thank you.